Okay, ladies and gentlemen, so the text on the screen today, understanding how bad the exponential distribution is. Now, my challenge today, I'm going to launch straight into this conversation, is I'm going to somehow weave into today's webinar this guy here, the naked mole rat, one of the ugliest creatures known to humankind. I'm also going to try and weave into the narrative a coffee mug. So there's two things I'm trying to weave into the story. The third thing I'm trying to weave into the story is a radioactive atom like this one. The third flavor of today's story, and the fourth and final flavor of today's story is going to be this: compound interest when it eventually comes up. Why isn't it coming up? There we go. So they're the four things that I'm going to somehow, my challenge is to try and weave those things into today's conversation in a way that makes sense and is otherwise going to help us illuminate look at why the exponential distribution really struggles. Okay, when we talk about this stuff, when we talk about randomness, most people already have an idea of what random is. I can just see in the comments, Bert, I just realized that web book I possibly have given you, I forgot to change the cover for that workbook from my typical course. So what I might do is have a look at that workbook after this and maybe change the front page. But what I suspect has happened, Bert, is that the content, is relevant. I've just forgot to change the title. So my apologies. So if you get downloading the workbook, like I said, if in many other webinars, if you are able to tolerate or revel in rank amateurism at this end, well, I'm the webinar host for you. So I'll try and fix that after this webinar. Now, the webinar we're talking about today, or webinar today, is all about randomness. And when we talk about what random is, a lot of people, so people on the street, have at least an idea they'll tell you about when it comes to describing what something random is. So, for example, if you walk up to a random person in the street and say, well, what does random mean to you? A lot of people will say things like, well, I think something is random if it has the same likelihood of occurring on any given day. Okay, that's random. Can't deny that. But when we talking about specific events, let's just say we have we're looking at a timescale of 1 year. And if we're trying to understand the likelihood of an event occurring on any given day, and this vertical axis represents the magnitude of that event, and if we're looking at how likely something is to occur over 1 year, then we know that because there's 365 days in a year, there's a 1 in 365 chance of that event occurring on any given day if it's equally likely to occur on any given day, and it can only occur once, which is what happens in the world of reliability. So if we look at a product, something that will eventually fail, a vacuum cleaner, a car, a space shuttle. Well, each space shuttle a space shuttle is probably not the best example because for lots of reasons, but if your vacuum cleaner fails in the world of reliability engineering and probability statistics, that is an event that you typically don't come back from. You often don't repair modern vacuum cleaners. Once they fail, people often move on. So if you can tie this to the whole concept of reliability, and where a failure event usually occurs once for many systems, and of course there's repairable systems and all the rest, but just bear with me for this analogy. If you think that something is random, can only occur once, then we know that if it's going to have an equal likelihood of occurring on any given day, the magnitude of that probability is 1 over 365. And now if we could visualize or represent that probability over the entire year, well, that's what it would look like. You'd have this very flat shape representing the fact that there's a 1 in 365 chance of something happening throughout that year if it can only happen once. Now, of course, that choice of 1 year is somewhat arbitrary. So if we said, you know what, I'm actually not interested in 1 year as my interval, I'm actually more interested, say, for whatever reason, in 2 years. And what is random? Random is something that has an equal likelihood of occurring on any particular day. Well, now if our interval of interest is 2 years, our probability of that thing occurring is now dropped to 107, 1 over 100, so 1 over 730. Okay, so you can see that depending on the interval which we're interested in, the likelihood of something happening, if it satisfies that original definition of random, is going to drop. But obviously 2 years is just as arbitrary as 1 year. So let's say we zoom out like a lot, and we're going to look at a period of 40 years. Well, if we're looking at something that has a chance of occurring once over a period of 40 years, and it's random, as our young gentleman suggested at the start of this conversation, well, the chance of it happening on any one day is 1 over 14,600. And so we know that when it comes to this sort of definition of random, where an event can occur once, or a ball bearing will fail once before it is removed from the system it's installed in. If you think that for something to be random, it has to have an equal chance of occurring on any given day, well, unfortunately, that also means you have to define the interval over which that probability is going to occur. So in this case, it's 1 year. And this also means that if you specify this interval, you're also implying that there is no chance of it occurring after the interval has finished. So after 1 year, according to this little visual, there is absolutely no chance of the event in question, the failure of a ball bearing or something similar, occurring, according to this visual. Now, we know nothing genuinely fails like that. Nothing genuinely fails with this probability is described by a flat rectangular shape, which doesn't change over a particular interval. And once that interval has expired, the probability drops to 0. So maybe the next go at trying to describe what random is in the world of reliability engineering, at least, is perhaps something is random if something fails randomly if it has a constant failure rate, I think. And this is one of the many ways people tend to describe random. So, for example, when we talk about something with a constant failure rate, people will say, oh, that means that the failure is 100% random. Well, actually, every failure is random. But so I know what they're trying to say, I believe, and let's just try and pick at that scab. See what people who think, well, when something has a constant failure rate, that means it is a completely random failure. Some of you might be going, well, what is a constant failure rate? So something that has a constant failure rate, if it fails at a constant rate. Okay, so this is not groundbreaking semantics, but to understand what it looks like if something has a constant failure rate or something fails at a constant rate, let's look at how something grows at a constant rate, which is why I introduced the concept of compound interest. Now, let's just say you have some money and you're going to invest your money into a savings account at a bank, and you have somehow been able to score an amazing annual interest rate of 24%. So your money is going to grow at a rate of 24% per year. And you start with $1. So obviously we have somehow found $1. We're going to try and understand what our money looks like over a period of 10 years. So on this slide on the screen right now, you can see a horizontal line going from 0 up to 10 years. We're going to add a vertical, not horizontal line, horizontal axis. We're going to add a vertical axis, $0, $1, $2, to represent the amount of money we have. And like I said, let's just say we start with $1 at time 0. Now, if we have an interest rate, an annual interest rate of 24%, that means that after 1 year, we are going to be paid interest in accordance with that interest rate, which is 24%. 24% of $1 is 24 cents. So now we have $1.24. Fantastic. Now we're starting to make some real dough. Now we can leave this money in our savings account. Oh, I got ahead of myself, which is, like I said, if you enjoy rank amateurism, this is the webinar host for you. You can see that this line on the chart represents 24% growth after 1 year. Of course, we can leave our money there, and after another year, we will get some more interest paid into our account. Now we have a total of $1.54. And that represents growth of 24% of $1.24 or 30 cents. So you can see that because we have more money in our accounts, the interest rate hasn't changed, but the interest rate of 24% is now, instead of being applied to $1, is now applied to $1.24. And so the amount of interest the bank pays us is more than it was last year. This is what compound interest looks like. The money grows on money that has already grown. And we can keep doing this, or keep predicting how much money we're going to make year after year. In this case, you can see that we have predicted that we're going to have over $8 after 10 years. You can see how our growth is starting to accelerate. The growth curve, as you can see on the screen, the growth curves up because money grows on money that has already grown. So that's interest that is compounded or put into our bank account every year. So every year, 24% of the balance is added. So this is what it looks like when interest is compounded annually. But we can also, if we want to, or if we find the right bank, compound interest every 6 months or half year. So that means the interest rate doesn't change, 24% annual interest rate doesn't change. But what the bank will do in this case, if we're going to compound every 6 months or half a year, is have half of the interest applied every half year. So 12% is going to be added every 6 months. This still is, in the world of bank speak, I suppose, this still would mean that we have an annual interest rate of 24%. It's just that half of that interest is going to be applied every half a year. And that changes how much money we have over time in a positive way. So you can see this red line here represents the projected growth. If we start with $1, well, you have 12% growth every 6 months. And you can see in comparison to the other faded red line, which is the growth we got if we compounded our interest annually, that we actually have a good deal more money as a result. So if you want to grow your money faster, ask your bank to compound more frequently. As a rule, most banks will tell you to go away because they're banks. But let's just say in this make-believe world, if you could ask your bank to compound at any interval, ask them to compound their interest payments more frequently. In fact, if we, instead of compounding every 6 months, we can compound quarterly, where we have 6% interest added every 3 months. You can see that the growth curve still curves up, but now we have even more money. And that's when we compound interest quarterly. If we compound interest monthly, where we had 2% added every month, again, we get more growth still. And the curve is starting to be less steppy and more smooth. Let me know if my technical jargon is getting is confusing anyone. Now, some really smart people said, hang on, what would happen is if we had continuous compounding? What would this curve look like if we compounded every nanosecond? We divided 24% down to the nanosecond level, or a really small amount, a really small time period, and essentially continuously compounded with an annual interest rate of 24%. They worked out that you could work out what that line was. And here, this blue line represents what growth would look like if you compounded continuously. That is, the interval over which you compounded was so small that you couldn't really tell if there was any steps involved. And some really smart people have worked out how to describe this growth curve based on any interest rate, including our interest rate of 24%. And when these smart people did this, they realized that they had to use a special number. This special number was 2.71828, and you raised the power of, in this case, 0.24, representing 24%, multiplied by t, or time. And so this equation here gives us the line that would represent continuous compounding. Now let's look at this number in particular, which is a really weird number. It's a special number, and no one knows why this number works. No one knows exactly why it's 2.71828. We don't know why it works for modeling continuous growth. We know that it just does. It's quite a famous number, but it's also got lots of digits. In fact, it's got an infinite number of digits, and these are just some of the digits. So you can see it's a really weird special number. It's very useful for modeling compound interest, and it actually has a special symbol, the letter E. And this number is known as Euler's number. And the reason why is because Euler is the last name of this Swiss mathematician and scientist, Leonhard Euler, and that's how you pronounce his last name, or at least it's this Australian's attempt at correctly pronouncing his last name. In this diagram is genuinely representative. You can see he has a droopy right eye because in that eye he was blind. Now, he didn't invent this number. A lot of people before him had used this number to solve problems, but he was the first one to represent it with a symbol, the letter E. And as a result, this number is credited to him. And no one knows why he used the letter E. Maybe it's because it was the first letter of his last name, but because he was the first one to give it a symbol, the letter E, it's since been known as Euler's number. Okay, so a lot of you might be pulling out your hair saying, fantastic, this is great information for how things grow at a constant rate. But I thought this is all about reliability engineering. Well, that's growth. But let's now talk about things that decay. Bear with me. Just to understand that this lunatic sometimes has a strategy. You're going to work out if a day is one of those days. So let's talk about things that decay. So in particular, radioactive decay. Now, here is an atom which has a bunch of protons and neutrons in its nucleus, surrounded by electrons. And radioactive decay involves atoms splitting into two smaller atoms while ejecting all sorts of nasty stuff and energy, which we can often harness for nuclear power generation. But it also ejects radiation, often harmful radiation or particles, which can do bad things. Now, radioactive decay occurs at a constant rate. And that means that if I was to get a bunch of radioactive atoms and put it in some sort of container, I'd be standing a long way away. And if I was to somehow be able to measure how many atoms are left in this container over time, and I knew how quickly these things were decaying, so let's just say these atoms decay at a rate of 24% per year, I'd be able to predict how many atoms or what percentage of unstable atoms remain over time. And this blue line would represent the expected percentage of atoms that are left behind. And if you think about it, this is actually, in a way, the opposite of what's happening when we grow interest or grow our money using compound interest. Instead of there being constant growth, there is constant decay. And for the same reason, we can then use that really special number, Euler's number, 2.71828, followed by lots of other numbers, to create this line, which represents the rate at which our radioactive atoms are decaying. There's one key difference in the equation, and that is this negative symbol. This negative symbol turns growth into decay. So the equation which describes this line is E to the power of minus 0.24, because for some reason, for whatever reason, we've studied this atom and know that it decays at a rate of 24% per year, multiplied by T, where T is the time in years. So E is very helpful. Euler's number is very helpful for compound interest modeling. It's also very helpful for modeling the decay of radioactive atoms. And you can also see how the decay curve slows down, because as more atoms decay, there are fewer atoms left to decay. And so the rate at which the percentage of remaining atoms reduces itself tends to slow down. And so this curve represents how radioactive atoms fail. And it's got a couple of really cool note that thanks, Sam. Anthony will have a chat after this conversation about how radioactive decay is the way I'm teaching is incorrect. Good for me to know. But when we look at these the way the radioactive atoms decay, we can see that if we were to look at how long it takes for half of these atoms to fail, and in this case, that would, if we look at this blue curve, it tells us that we have a half-life of what we call a half-life of 2.89 years. That's the time over which we expect half of our atoms to fail, or not fail, to decay through radioactive decay. I'm using the word decay a lot. I'll try and get on top of that. So in this case, the blue line tells us that after 2.89 years, we have 50% of our original atoms, unstable atoms. Okay, well, that's interesting. But what that also allows us to do, or what we also find, I should say, is that if we go another 2.89 years after that, then we have 50% of the 50% of the remaining atoms remaining. And if we go another 2.89 years after that, then we have 50% of the 50% of the 50% of the original atoms remaining. And what that allows us to do is use this, what we call half-life, to predict when we'll have 50% of the original number of atoms remaining, 25% of the original number of atoms remaining, and 12.5% of the original number of atoms remaining. And this is exactly what the decay of polonium-208 looks like, because it has a half-life of 2.89 years. And so this just is another way of understanding why this decay curve tends to slow down. The rate at which the curve goes down itself slows down. So we use the term half-life for radioactivity because it's just found that every additional step we take, which happens to be the half-life, will essentially halve whatever remaining atoms we have left. So it goes from 100 to 50% to 25%, 12.5%. And there's a reason why we use this term half-life. It's because radioactive atoms, including polonium-208, essentially never age. What does that mean? Well, what it means is that if you have a polonium-208 atom, it doesn't matter how old it is or how young it is equally likely to decay today as any other day. And that's an interesting concept to wrap our head around. Even though we know that as these atoms get older, they are more likely to fail, they don't ever age, which sounds counterintuitive. But all that means is that if you were to put two polonium-208 atoms in front of anyone, we would be able to tell how old they are, because their characteristics don't change. And yes, as time goes on, they're more likely to decay, but there is no inherent clock or wrinkles or damage or birthday, which allows us to work out how old these atoms are. It doesn't matter how old or young they are, they look exactly the same and are equally likely to decay on any given day. All right, so I'm torturing you with concepts regarding compound interest and radioactive decay. So what does any of this have to do with reliability, which is my lead into the third element I talked about at the start of this today's webinar. Now, believe it or not, reliability engineers like Fred and I have absolutely scintillating conversations in our free time, which includes pondering about trying to imagine or brainstorm items or products or systems which also never age. And one of the most common conclusions or common items we brainstorm that satisfies this criteria is the humble coffee mug. Because as near as we can tell, coffee mugs never age, at least from a reliability perspective. Now, of course, coffee mugs often have paint on the mug themselves. The paint itself can degrade and fade over time. So yes, you can look at paints and whatever you use to paint your coffee mug with. And yes, those colors will change over time. But let's look at the actual structural integrity of a coffee mug made out of ceramic. And there's a reason why archaeologists through ancient Egypt and Mesopotamia and all those ancient civilizations across the world will find ceramic pots and jugs and everything else in essentially pristine condition. And that's because ceramics are very strong and stable. Their strength doesn't degrade over time, but they will fail as a rule if and only if we drop them or the ceramics are damaged from external events. And that means that from a reliability perspective, things like coffee mugs never get old. If we assume that the only way they fail is if they break when people drop them. And the reason why we can say that they never appear to age is because it doesn't matter how old this mug is or how young this one on the right is, they are both equally likely to be dropped by the klutz human who's using each coffee mug to drink their liquid for that particular day. And so coffee mugs are examples of items that appear to fail with the constant failure rate, because their chance of surviving today is not dependent on how old each mug is. But this is a bit of a rarity in the real world. But let's just say that we can satisfy to ourselves that coffee mugs only fail at a constant rate. Well, the good thing about that is all the stuff we learn through compound interest and radioactive decay means we can model the percentage of coffee mugs we expect to be surviving over time using exactly the same formula that we used to generate or model the decay of radioactive atoms. In this case, you can see the chart. The vertical axis is reliability, the probability of something still working at a particular point in time. And the equation for this curve is Euler's number 2.71828 to the power of negative lambda multiplied by t. That negative symbol represents the fact that our curve is decreasing. It's not decaying in the radioactive sense, but in a way it is decaying in that it's going down. And we have lambda here, which is the Greek lowercase letter, lambda, representing what we call the failure rate or the hazard rate. And so if we can borrow what those geniuses of centuries ago came up with to model compound interest, we can take the outputs of their study to create this equation here, e to the power of minus lambda t, which is the reliability equation for our coffee mug. If we can somehow characterize the failure rate of coffee mugs, i.e. somehow characterize the rate at which coffee mugs are dropped by the klutz humans using them, we can create this equation here, which gives us the reliability of our coffee mugs over time. But this reliability function can be hard for us to understand when it comes to trying to at least visualize the random nature of the failure it describes. So let's look at a different reliability curve to see what this lunatic's talking about. So here's another reliability curve, and this reliability curve is it has a corresponding what we call probability density function or probability density curve. The probability density curve at the top is something we are very comfortable with as a rule. So it's like a bell curve. It's not a perfect bell, but you can see the red line at the top has a curve which helps us visualize the likelihood of a random variable having a particular value. It has a corresponding reliability curve at the bottom, which sort of has a shallow slope at the start, a steep slope in the middle, and a shallow slope at the end. And the reliability curve and the probability density curve, for in this case, something that fails, this is based on a roller bearing, that you can see the time to failure is on the horizontal axis at the bottom. They encode exactly the same information. They encode how something fails in a random way. And in fact, you can use the probability density curve to create a reliability curve and vice versa. So for example, if we trace out our reliability curve, you will be able to see that it corresponds with the area under our PDF curve to the right of the particular time to failure. So let's visualize what those words I just spewed forth actually mean. So you can see right now, we're going to trace our reliability curve from the top and stop right there when the reliability drops to 60%. Now you can see this point corresponds to a certain fraction of area under our PDF curve. And that fraction of area happens to be also exactly 60%. So this is how reliability curves and PDF curves encode exactly the same information. They have the same information in their shapes, but they visualize what's going on in a very different way. The probability density curve is, as a rule, how we like to visualize randomness, but the reliability curve is really much more useful if we're trying to get actual numbers to make decisions. And if we were to keep tracing out the area under the curve as we move from left to right, we complete our reliability curve. So each reliability curve has a corresponding probability density curve. In this case, that probability density curve has a peak, which aligns with how we like to visualize randomness. But let's go back to the reliability curve for our coffee mug, and we'll create our probability density curve based by tracing out our reliability curve. And when we do that, we get something a little bit unexpected. And that is our probability density curve doesn't have a bell shape, doesn't have a peak. In fact, it has exactly the same shape as our reliability curve. And that doesn't make any sense at all to our primitive conscious human brains. They have exactly the same shape, but that doesn't look right. In the real world, it actually is. It's not a bell shape at the top, but they have the same shape with the reliability curve starting at 1 or 100%, and the PDF curve, the probability density curve, starting at lambda or the hazard rate. That's the only difference between the two. This is a very unique example where the reliability curve, the probability density curve, has the same shape. And that probability density curve doesn't have that bell shape we like to use to visualize uncertainty. So this doesn't gel well with our primitive understanding of how the real world works. But that's what it looks like when things fail at a constant hazard rate. And so there's our equation for reliability at the bottom left. And here is our equation for the probability density function, which gives us this curve. Ooh, at the top. It's exactly, come on, computer. You can see it's exactly the same, except that there is a lambda at the front. Let me see if I can get my computer to be a little bit less anxious to move on to the next slide. Bear with me. Like I said, I hope you can tolerate / enjoy amateurism. So the probability density function is exactly the same as the reliability function, except that it has the hazard rate added to the front. Now, this is the simplest probability distribution in the world, and it is useful for modeling things that are just as likely to fail when they are old as when they are young, or for things that never age. And this probability distribution has a name. Let's see where this name comes from. So let's go down another rabbit warren, or another naked mole rat hole. Let's say that this letter X represents some number. Most of us would know that if I put this number 3 next to this letter X, that number 3 is what we call an exponent. So we have X to the power of 3, or X raised to the power of 3, or X cubed. And all this means is that this symbol tells us that we are wanting to multiply X by itself 3 times. And so this is an example of an exponential function because it involves that exponent. And the exponent can change to whatever number you're interested in, or you can change what the input argument is for this exponential function. So sometimes instead of having X, we use things like the letter E. Oh, come back. Oh my God. What is happening here? And so what this means is that this here, let me get back on track. Try and say interesting things to keep the team interested. Bear with me. So if this is what we call an exponential function, you can see it's structurally similar to the functions we used to create the reliability and PDF functions for that coffee mug. And for this reason, the probability distribution based on those equations is what we call the exponential distribution. Sorry for having some technical issues at my end. So this is the exponential distribution as a result of that function being called the exponential function. All right. So what has any of this got to do with that ugly creature we looked at the start of this lesson? That is the naked mole rat. The naked mole rat is one of the very few creatures that never ages. It never wears out. It never accumulates damage. It doesn't suffer from heart disease or cancer or anything else that involves the accumulation of damage over time. And scientists are studying the naked mole rat to see how it somehow manages to essentially be free of diseases that we would associate with us getting old. Doesn't mean this thing is immortal. They have they're very long-lived rodents, to be sure. They can essentially live decades, but when they do die, it's because of predation. They get killed by predators, which is equally likely regardless of age. It's an incredible creature, and with this characteristic obviously being very, very, very rare in the animal kingdom. It can survive on really low levels of oxygen. It metabolizes things in a very different way. It's one of the few creatures which can move just as fast forward as it can when it's walking backwards. But and it's also like an ant society. It has a queen which is bigger than the rest of the naked mole rats in its colony, and the queen maintains its status by essentially bullying every other rodent it has in its brood. So it's a very unique creature, but it has this incredible characteristic where it never accumulates damage. It's able to repair its DNA molecules in ways that make scientists very, very interested. So it only dies when it gets eaten by something or it gets injured by a rock falling on top of it, for example. So it doesn't matter how old or young it is, it's equally likely to die today as it is tomorrow or 10 years from now. But that means that there is something we need to be aware of. There are no systems out there which are more complex than coffee mugs or that are not made out of ceramic that have nothing but a constant hazard rate. But there are systems that have some failure mechanisms that fail in this way. So what this means is that virtually every product or item out there will have things or components that do wear out. It's crazy to assume otherwise, but there will be some failure mechanisms in complex components and systems that do have this constant hazard rate characteristic. So, for example, here is the smart lock, which most of you will be getting tired of when it comes to these webinars, because I use this all the time as my central example or central system to base my discussions on. And one of the things that can ruin the day of electronic systems and products like this is what we call electrostatic discharge, where if we live in a dry environment and we shuffle our shoes along a carpet and we grab the handle, the static electricity built up in our body can spark or leap across a gap to the thing we're about to touch, which in this little spark involves thousands of volts, which is very short in duration in terms of the flow of electricity, but enough to ruin the day of sensitive electronic components within our product or our system or our item. And so that means that if we explode our smart lock into its constituent subsystems and components, and we zoom into the subsystem which is going to be potentially ruined by electrostatic discharge, which is the PCB, we could have a problem. If we haven't taken due care when we design our PCB, there's a chance that electrostatic discharge could turn a healthy conductor path on our PCB to a damaged one. It's very, very easy to damage conductors or components on PCBs through things like electrostatic discharge. Now, if this is the case, obviously you can see that it really doesn't matter how old our smart lock is or how young our smart lock is, it's equally likely to fail from ESD because ESD is caused by those events or scenarios where human beings, for whatever reason, gather enough static electricity in their body to create that spark when they grab that handle. So that's an example of a failure mechanism that can essentially have a constant hazard rate, even though it is relatively rare. So let's do some revision on what we've done so far. We'll revise some stuff. This is a sort of statistics conversation, but we'll have a look at the exponential distribution and to sort of summarize what we've covered so far. So here is our probability density function. which is represented by the function f of t equals lambda e to the power of minus lambda t. You can see we have this unintuitive curve on the screen, which has the same shape as a reliability curve. Now, the PDF allows us to create or draw the CDF, which is the cumulative distribution function, the area under the PDF curve, which represents the rate or the failure probability of our item at a particular point in usage. And we can easily essentially get the area from our PDF curve to create this line here, which represents the failure probability of our smart lock, or sorry, our coffee mug over time. So that's a CDF. Now, all the CDF is 1 minus a reliability function. If you go to the reliability function, the probability that something has not failed at a particular time of usage in a specified condition, 1 minus a CDF. So the reliability curve is essentially the CDF turned upside down. There's our reliability curve right there. So that's our reliability function for our exponential distribution. There's its equation, e to the power of minus lambda t. And of course, last but not least, the hazard rate for the exponential distribution, the failure rate, the rate at which a surviving system fails, stays constant the whole time. So that's the hazard rate for this particular exponential distribution. Now, that is a very important thing to understand. When the exponential distribution is used, you are assuming that the thing you're modeling never gets old and never gets young. And of course, that does not apply to very many scenarios or very many systems at all. Now, before I finish torturing you with statistics and stuff, let's look at the mean time to failure. So for those who've done previous webinars, you know what the mean time to failure is. For those who are new, the mean time to failure is going to be easily found if we can find that probability density curve. So here is an example of an exponential distribution, or a bunch of exponentially distributed random variables. Each blue dot represents perhaps the time to failure of a particular coffee mug. And this is how our brains, but this curve here is how our brains tend to prefer to characterize uncertainty or randomness. We like to look at a random variable as if it has some sort of central value around which it is more likely to occur, and that value becomes less and less likely as we move away from our best guess or that central value. And this is not what the exponential distribution looks like at all. The probability density curve is anchored on that vertical axis as described by this equation here, where lambdas are that hazard rate, the failures per unit time. Now, the failures per unit time can be used to help us find the MTBF. So if the lambda represents the failures per unit time, then 1 over lambda is essentially the unit time per failure, or the expected time between failures until the next failure. And that is the mean time to failure. So the inverse of the hazard rate is the mean time to failure, which allows us to find the mean time to failure for this exponential distribution, which we all know is also the balance point of that probability density curve shape. You can see the balance point has been added to the screens, and that's the mean time to failure, or 1 over the hazard rate for our exponential distribution. And for our exponential distribution, that means that we can look at our PDF curve and work out that 63.2% of our random variables will have failed by the mean, regardless of where that mean is. So even if the mean is shorter or higher, or bigger and smaller, no matter what, 63% of our coffee mugs will have failed by the mean time to failure. So this applies to things that fail due to environmental stresses like human beings dropping the coffee mugs, or tornadoes, or thunderstorms, or tsunamis, or voltage spikes, or things that will occur in a completely random way with respect to the age of our system or our device. Doesn't matter how old or young it is. If it gets hit by a tornado or a lightning strike or a tsunami, or if our car is driven into a tree, or if we have a voltage spike, age is irrelevant. It's going to ruin the day of our item. Another way that we can look at this, for those who've heard of stress strength interference, this is what it looks like if the strength of your item doesn't decrease over time. That is, it never gets old. It doesn't accumulate damage. So ESD is an example of of how something can fail with a relatively constant hazard rate. But there is a problem. And that problem is that the exponential distribution is simple, usually too simple, but people crave the simplicity associated with it. So let's look at how this can go bad or this can go wrong. We're going to look at a diode. This is a diode, which is a fantastic electronic component. What the diode is supposed to do is ensure that electrical current is only allowed to flow in one direction. So if current's going from left to right, that's great, but the diode will stop current from going from right to left. Now, this diode is advertised with a hazard rate of 100 fits. What is a fit? That sounds like a psychological condition, but in this context, in the electronic consumer product industry, or electronic component industry, I should say, one fit is, or a fit stands for failure in time. One fit is equal to one failure per billion hours, and that is, yes, a very long time. So the manufacturer, the OEM, tells us this diode has a failure rate of 100 fits, 100 failures per billion hours. Now, because this is the only parameter that our manufacturer or OEM has given us, people tend to assume the exponential distribution is used to model its reliability. The exponential distribution is the only distribution, the only probability distribution that can be defined using a single parameter, which includes the failure rate. And that is a problem. So sometimes we get these single parameters from our suppliers. We go, well, okay, well, without me having to think about it, I have to use the exponential distribution. So let's look at what that means for our diode. So if the failure rate is 100 fits, which is equal to one failure per 10 million hours, or one failure per 416,667 days, or one failure per 1,141 years. That's what that failure rate is implying. That's our best guess. Our expected number of failures every 1,141 years is 1. So 1,141 years is actually the mean time to failure for this diode if it does indeed have a hazard rate of 100 fits. Now, this is clearly incorrect. Diodes as a concept have not been around for more than 150 years tops. To say that we can say that we're going to expect a diode to fail once every millennium or more is absolutely crazy. We know this. We know that diodes are not going to last this long, but we still have, for whatever reason, OEMs telling us that this component has a failure rate of 100 fits. In fact, some components are advertised with failure rates that can be as low as 10 fits. And that implies that there'll be one failure every 11,000 years, which is absolutely crazy. So let's look, but let's just follow this example through. Let's just say we're interested in finding the reliability of this diode after 1 year. Now, if we assume that the time to failure is modeled with the exponential distribution, we can use the reliability function we just looked at, replace t with the number 1, because it's 1 year we're interested in. We know that the hazard rate is the inverse of the mean time to failure. So we can replace lambda with 1 over mttf, which in this case is 1,141 years. We can evaluate this equation to tell us that there is 0.9991 chance of our diode working after 1 year, or a 99.91% probability of our diode working after 1 year. Okay, all right. Seems plausible, I suppose. But how can this diode have an MTTF of 1,141 years? How can the OEM have the nerve to tell us that there is this has 100 fits failure rate, which implies that this thing is going to last longer than most empires or most civilizations have in the history of humankind? We know that electronic components will eventually wear out because of the due to the accumulation of damage. In particular, diodes, which involve silicon crystals and the rest, eventually you will have things like diffusion, where conductive atoms migrate through the silicon crystal, or you will have dendritic growth, or you have other things, or things that are caused by, let's call it wear and tear, mean that cause this diode to wear out, which means that eventually the hazard rate is going to increase as more and more damage is accumulated. So we know that electronic components will, if they eventually wear out, they cannot be modeled with an exponential distribution. But yet we have OEMs and manufacturers telling us or selling us that try and peddle this lie that we can use fits to describe their time to failure. So why is this? The reason is that even though we know that electronic components will eventually wear out, usually with a probability density curve which looks something like this, after a certain period of time, you can see the hazard rate is very, very low until the damage gets to some critical threshold, which causes ongoing, or where the risk of failure starts to increase. The OEMs and the manufacturers only ever test diodes in this beautiful young phase where those wear out failure mechanisms have not kicked in. And so they test these diodes where diffusion and dendritic growth haven't started to increase the risk of failure. And they observe the number of failures on those test beds for that relatively short period of time, do the math and say, okay, this implies a failure rate of 100 fits. We'll put that on the box and sell these diodes. But that unfortunately tells you precious little about how long the diode will actually last. And so even though we know this is an issue in the electronic component industry, there is not a lot of motivation to change it, because that's just how things have always been done. So it's incumbent upon us to realize that there are people and industries and companies out there which will assume the exponential distribution is true or correct when it suits their commercial needs, which, when it comes to electronic component manufacturers, they are not motivated at all to characterize how long it's going to take for their diodes to wear out. They want to be able to say that this has a failure rate of 100 fits, which means we expect one diode to fail every 1,141 years, which we know is incorrect, but they would prefer to peddle that myth as opposed to be upfront and honest about how long that diode will actually take before it fails. And that's where us reliability engineers need to understand when the exponential distribution should and should not be used. But the final message for today's conversation is that we are not here to admire problems. If we go back to our issue where our smart lock might be failing due to electrostatic discharge, or ESD, there are things we can do to protect our precious electronic components. And one thing we can use is what we call a varistor. A varistor looks like that, which looks like a surface mounted resistor, and in a way it is. But a varistor, which stands for variable resistor, is actually a really cool little component. And what the varistor does is it allows us to essentially connect it to the main circuitry on our PCB. And when there is low current or low voltage electricity traveling around our circuit, which we want it to do, that's usually involves the signals and everything else in our smart lock to tell the motor to start unlocking the door and everything else, our varistor sits there and does nothing. And the reason why it does nothing is because when there is low voltage, our varistor has a very high resistance. It essentially stops being a conductor. However, if we have an ESD incident, which means that we have an incredible amount of voltage perhaps making its way to the PCB, with an incredible amount of voltage traveling through our circuit, when it hits our varistor changes characteristics. When there is high voltage, the resistance of our varistor drops by an incredible amount. So all of a sudden, our varistor is the path of least resistance for our current, which has high voltage. And so instead of that high voltage, high current traveling to our delicate circuitry, it now goes through our varistor to some grounded component of our smart lock, saving the day. So this is an example of a component which can address a particular form of constant hazard rate failure. So That's on that note. I'm going to finish the discussion there, and I can see that Danny has his hand up, and I'll ask that. I'm more than happy for you to answer your question, Danny. If you want to type your question in the question box, or where are we? Where are the questions? Or just in the chat window, I'll do my level best to answer that question. But to summarize, the exponential distribution is really, really simple. Too simple. It can model things like how many radioactive atoms we expect to still be around after radioactive decay. It can also help us characterize how many coffee mugs we expect to be in our office kitchen by the end of the year, if the only way our coffee mugs fail is through human beings dropping said mug, which is an example of how something fails in a way where it doesn't matter how old or young our coffee mug is, it's equally likely to fail on any given day. It can also model specific failure mechanisms like electrostatic discharge failure for our smart lock or other things like that. However, what it cannot do is model anything else that involves wear out or wear in or anything that challenges the baseline premise that the failure rate or hazard rate is constant. If you have infant mortality, that implies the hazard rate or failure rate is initially high and decreases over time. So the exponential distribution is not going to work. And also, if you have things that wear out because damage is being accumulated, then likewise, the exponential distribution does not work because the premise again is that the hazard rate or failure rate remains constant. And so the electronic component industry is a classic case study of how the exponential distribution is misused, and many bad decisions have been made as a result. So finished up a little bit early today. Sorry, I was teaching till all hours of the night last night, so my words in my mouth is not. I'm losing the ability to speak as we speak, as you can tell. But if there are any questions, please feel free to share them in the chat window, and I'll do my level best to answer them. See, Carl's giving us some background on what naked mole rat is and where Euler's number comes from. You're welcome, Carl. Any questions at all? Samantha asks, is it acceptable to use the exponential distributions for parameters other than time? For example, with the stress strength interference theory, we can use it, but translate it to meet the minimum expected stresses. So what I think you're asking, Samantha, correct me if I'm wrong, is you're asking if we can use the exponential distribution to characterize the distributed stresses and the distributed strengths. Is that correct? Cool. The answer is no. And the reason why is because you would the stresses and strengths of a component tend to cluster around a central value. So you would expect a bell-shaped distribution to model strength, for example. So the strength of a ball bearing you manufacture, it will, I know it's difficult to characterize the strength of something using a particular characteristic, but stresses and everything else, you look at yield strength of a steel member, for example. That yield strength will be consistently around some central value, and from steel member to steel member, there'll be some natural variation around that central value, which means we expect that bell-shaped distribution to describe the random dispersion or the difference from steel member to steel member that we get from said factory. So the exponential distribution can't do that. It has that weird probability density curve, which is anchored at the vertical axis. We would expect a bell-shaped distribution to do a much better job of modeling the strengths we would expect for our components. And the same thing applies to the stresses as well. Now, that's not always the case. And yes, you can have scenarios where you'll have lots of smaller stresses, fewer bigger stresses, and even fewer bigger stresses beyond that, which sounds like it has a more exponential distribution. But as a rule, you would expect a distribution called the log normal distribution to do a much better job of modeling the stresses that something's going to experience. But that said, You need to do some analysis to work out what distribution works for you, but almost certainly it will not be the exponential distribution. Does that answer your question, Samantha? Yeah, and as Fred points out, you can use the exponential distribution to model anything. It just might not give you useful results because it's not not reflective of the real world. Uh, Jesus asks, excuse me, how reliable is the estimation of fit values using standards such as SN29500 and also calculating reliability based on fit values? Very, very bad in both examples. So what that means, if you have this, every time you have standardized fit values for different components, essentially you take out of consideration the difference in manufacturing processes from manufacturer to manufacturer. And there are some manufacturers who do a way better job of manufacturing quality components and some manufacturers that don't. To have a single number which characterizes a type of component, regardless of manufacturer, is misleading. If you say you need to have a rough order of magnitude guess, then of course those numbers work. But if you want to have anything meaningful, you really need to understand your components. And as per the example we used for the diode, having those fit values estimate reliability is incredibly challenging to use in a useful way because electronic components wear out. And when you have those fit values, essentially they're modeling the pristine components before they start to accumulate damage. So it's a very, very misleading thing to do, to use the reliability function from an exponential distribution to model the time to failure of things like diodes. So hopefully, Jesus, that answers your question. Bert, all right, thanks. How do I communicate this to marketing design engineers and engineering managers? Well, the webinar is recorded, Bert, so you can let them know. All they need to do is become a member of Ascendo Reliability and can see the webinar for free. Of course, you might have a relatively low uptake rate, but hey, if there's any messaging, feel free to send me an email after this and we can see what we can do. Any more questions? Another example where the exponential distribution works is where we're modeling things like the reliability of tires which fail due to punctures. And that's kind of a big deal on mining sites, for example, where tires, depending on the nature of the roads, tires don't wear out because they're being punctured so often because the roads are poor quality that the time to failure for a tire is best modeled with a constant hazard rate. And punctures will obviously ruin the day of a tire, regardless of how old or young it is, when I'm talking about punctures caused by sharp rocks or sharp objects. So there are scenarios where the exponential distribution can work. You just need to make sure you know if it can work before you use it. Any more questions?
Yeah. Hey, Chris, I was going to jump in on Bert's. There's a great way to communicate it is to model it appropriately. Let's say you have a time to failure data set and it's, say, a Weibull distribution of some sort. Model it that way and see what the probability of failure is over, say, your warranty period. And then also look at modeling that same data with an exponential and see how different they are. And would that change the decision to do something about fixing your product or not? It's a start to say, if we fit, if we treat our data accurately and model it accurately or better than what we have been doing, we can make better decisions. And that's one way to get the point across, is that the way we model the information matters.
Another way you can maybe put it to them, Bert, is say, well, this diode, which has an advertised failure rate of 100 fits, that implies a mean time between failure of 1,141 years. Do you think that's going to work? Yeah. Do you think that's right? So it's not exactly the same thing Fred's talking about, but in a way it is, in that you're saying, well, if this is true, this is what it means. Do you think that's that's rational or not. And hopefully they'll say, no, that's not rational. So, okay, well, let's move on. You can see Carl writes that he's talking about how the exponential distribution models the amount of time between independent events. In this type of study, the probability density function assumes that the events occur at a constant rate. So just to, yep, okay, I'll take that point. You're talking about a homogeneous Poisson process. So reliability analysts use this distribution to model failure times. So I think the thoughts on that topic, Carl, would be sort of the gist of the entire webinar, that yes, you can use the exponential distribution if you want to, but it might be modeling something that's not your system. I'm modeling something you prefer to model because that's easier to model. So when you're talking about the time between subsequent independent events, that is the Poisson process. And that can work if you're, for example, trying to understand how many cars are going to drive past you in a particular hour. For example, where the likelihood of a car driving past you does not affect the likelihood of the next car driving past. That's what we call a memoryless or ageless scenario, again, analogous to the naked mole rat. But in the real world, when it comes to reliability stuff, that scenario is quite rare. Coffee mugs are not much else. Have we thought of anything besides coffee mugs, Fred, or is coffee mugs it?
Yeah, I used to think fluorescent lights were that, and then I learned that fluorescent lights decay. And LEDs also, they last a long time. You get plenty of light out of them, but the LED element itself will age. It will
Yep.
lose its power to create illumination over time. And it's a slow process, yet it does occur. And at some point, it's not enough to read your morning paper.
And the LED itself is usually embedded on a silicone crystal, which, as we know, accumulates
It has its
damage.
own problems. Yep.
I think we might have exhausted the attendees regarding questions.
Oh, Samantha's back with your radioactive decay thing.
Okay, so it's very nitpicky, but the description that it splits into, oh, there we go, into two complete atoms is actually describing a specific process of spontaneous fission, which is a type of radioactive decay, but one of the least common types. Much more common is alpha, beta, or gamma photo energy decay. Yes, and I'm aware of that. In fact, the example I was using was an example of beta decay in particular, where uranium will the byproducts of uranium will often, the fissile products themselves will undergo beta decay. Where beta decay, correct me if I'm wrong, involves three electron neutrinos, and it involves obviously heat. There's one other thing as well. There's three things. There are three things that come out of beta decay. But yes, I understand that there is things besides just those two atoms coming out of a split or a larger split atom as well. Yeah, I use beta decay in another course where I actually go through that in greater detail.
Yeah, I think that's where your graphic showed it, saying, well, you get two atoms, one lead and one silver or something like that. It's
Plus the radiation in between.
yeah, but usually it's a small bit of piece comes off and it says, and it changes its characteristics. It goes from being, oh, I'm going to throw this stuff away until I'm stable or become lead.
Yeah, yeah. And of course, I mean, you look with beta decay itself, where actually the atom doesn't split, it just changes where you have a proton turn to a neutron. And the fission itself is where uranium splits into those two.
Yeah, and that's where things get
components.
exciting.
Yeah, that's right. Yeah. No, I take your point, Samantha. So Carl writes, entropy naturally increases over time. Problems arise. Your house gets messy. Your garden gets squeezed. Then the heat from your coffee spreads out. Businesses fail. Crimes and revolutions occur. Good Lord. So we are covering a large gamut of outcomes and relationships. And I don't know if that would be associated with entropy increasing the relationships bit. Anyway, I'd say entropy decreases when your relationship ends. But anyway, in the long run, eventually in the long run, everything naturally decays and disorder always increases. Any thoughts?
Well,
Um,
let me answer that one, Chris. It's what
sure.
keeps us in business. I mean, we're reliability professionals. Everything fails eventually. At some point, the Earth is going to fail because the sun, you know, expands or blows up or does whatever it's going to do, or a great big meteor hits us. Everything fails. Um, and that just keeps us in business. The trick is knowing which ones matter, um, and which ones can we say, all right, we need to make a decision. Is this a 20-year product or not? Well, how do you know? Well, do you think the sun's going to fail in within 20 years? Well, probably not. We hope. But so just take that failure mechanism off the table. Let's think about, I think the way you phrase it, Chris, is what are the vital few? What are the things that are going to mess up the day of your system?
Yeah, and it should be uh the it should point out that every atom has a half-life. So some atoms, even the atoms we don't associate with being radioactive, the carbons, the oxygens of the world, they have a half-life. That half-life is often measured in the term in billions of years. They take that long for any sort of chance of decay to occur. That goes to the whole entropy piece. Yes, they will eventually undergo some sort of radioactive decay, but the reality is we don't really model that or worry about that too much because the rate at which those very stable elements decay is incredibly small that it doesn't matter. But that doesn't mean they're not going to decay along the lines of what you're talking about regarding entropy. It's all about working out what the vital few weak points are. And yes, everything's going to be turned to hydrogen eventually as the universe keeps expanding. But if it
Who
doesn't
cares?
influence a decision, it doesn't matter.
Yeah, who cares? The opposite of that extreme is if you're designing and building a product and somebody asks you what's the reliability of it, and you should ask, well, how long does it need to work? And well, for it just needs to work once ever. And in that case, well, you're using very, very stable elements that aren't going to decay too quick. Is it not going to rust? Is it not going to corrode? Is it not going to have UV radiation degradation? In which case, that if it only needs to last for 10 minutes and nothing in our environment or normal occurrences are going to decrease its ability to function, well, then you're probably pretty good. If it's only going to be exposed to those elements for 1 hour ever, and it's manufactured perfectly so that it doesn't have any latent defects built into it, and so on and so on. So even then, I still have struggles with saying that you can use the exponential to model it.
Yep. Concur. I just did a quick Google search. Apparently, tellurium 128 has a half-life of 2.2 times 10 to the power of 24 years, which is 160 trillion times greater than the age of the universe. So
Pretty stable, I think.
you'd be waiting a while.
Yeah.
Any more questions? I think our attendee list is decreasing or decaying at a constant hazard rate, but that rate is increasing.